Imagine you're trying to find the one perfect key to open a life-saving lock. Now imagine that key is a tiny molecule, and you have to search for it on a keychain that has more possible keys than there are atoms in the entire universe. That, right there, is the incredible challenge scientists face every single day. But today, we're looking at a brilliant new method that acts like a smart compass in that massive search. So let's get into it.
Here's how we're going to break it down. First, we'll get a handle on the sheer scale of the problem, what I like to call the molecular maze. Then, we'll look at the classic survival of the fittest approach and where it falls short. We'll see how scientists try to fix that by adding diversity. And then, the big breakthrough arrives, our smart compass, which combines the best of everything. Finally, we'll look at the proof and talk about what this all means for the future.
Just take a look at this number. That's a 1 with 60 zeros after it. To put that into perspective, that is way more than the estimated number of atoms in the known universe. This is the size of the chemical haystack we're sifting through. So it's not just about finding a needle in a haystack, it's like finding one specific atom in a universe made of haystacks. And that brings us right to our first stop, the molecular maze. The challenge is finding that one single molecule we need in a practically infinite chemical space. Seriously, it's less like finding a needle and more like finding a specific grain of sand on a planet that is nothing but beaches.
So to wrap our heads around this, let's use an analogy for the whole explainer. Think of this process as a massive treasure hunt. This chemical space is a huge, uncharted island. We're looking for a very specific kind of buried treasure, the perfect molecule. And the algorithms we use, those are our maps and our shovels.
Okay, so let's talk about our first tool. For a long time, one of the best maps for this treasure hunt has been something called the genetic algorithm. And it works pretty much like it sounds. It mimics natural selection, survival of the fittest, to evolve molecules and find the best one.
It's actually a pretty simple and powerful loop. You start with a bunch of molecules, you mutate and cross over them, basically you mix and match them to create new versions, then you test them all to see how fit they are, how close they are to what you want. And finally, you only keep the best ones to breed the next generation. Simple, elegant, and it works, but only up to a point.
Yeah, because there's a huge flaw here, stagnation. The algorithm gets fixated on a good enough solution. In our treasure hunt, it's like our explorers find a few gold coins, and they get so excited they just keep digging in that one spot, totally convinced it's the main prize, while completely missing a giant treasure chest just over the next hill.
So how do you fix that? How do you avoid getting stuck? Well, you add diversity. And that was the next big idea, the quality diversity fix. It's an approach designed specifically to force the search to explore the whole island, not just one little corner of it. Quality diversity, or QD, basically changes the goal of the game. Instead of looking for a single best molecule, it builds an archive of champions. It keeps track of the best molecule found for every different type of terrain on our island. The best one for the mountains, the best for the beaches, the best for the jungles. This forces the search to cover the entire map. And this really shows the difference, right? A standard genetic algorithm has a population. Everybody's fighting to be the one and only winner. A quality diversity algorithm maintains an archive, which is more like a hall of fame full of different local champions, each the best at its own thing. It values variety just as much as quality. But this created a new problem: inefficiency. Our treasure hunters are now exploring the entire island, which is great, but they're doing it randomly. They're just digging holes everywhere, wasting a ton of time and energy in places that any expert would know are totally barren. It's thorough, yeah, but it's painfully slow. And this is where the hero of our story finally arrives, the breakthrough. It's called Bayesian Illumination, and this is our smart compass. It takes the evolutionary power of the genetic algorithm, combines it with the wide-ranging exploration of quality diversity, and then adds a game-changing new ingredient, intelligence. Okay, I know this diagram looks a little busy, but it's really just putting all of our pieces together. On the left, you've got that mutate and crossover engine from the genetic algorithm. In the middle, you see that grid. That's the archive from quality diversity, making sure we explore everywhere. But the real magic, the new part, is over on the right, the surrogate fitness model. That is our smart compass. That's the intelligence that guides the whole thing. So how does this actually work? Well, it's a brilliant learning loop. First, we create new molecules, just like before. But, and this is the absolute key, before we do a full, expensive, time-consuming test, the smart surrogate model makes a quick prediction. It tells us, hey, these new molecules over here look the most promising. so we only spend our precious resources testing the top predictions. Then the results from that real test update the archive, and crucially, make the surrogate model even smarter for the next round. It learns as it goes. Okay, so this all sounds amazing in theory, right? But does it actually work in the real world? Let's look at the proof. The researchers put Bayesian elimination head-to-head against the older methods on a standard test, rediscovering a known anti-diabetic drug. It's the ultimate showdown. And the results are just staggering. I want you to focus on that middle column, AV fitness evaluations. That's the cost. That's how many expensive tests each method needed. The original genetic algorithm? Over 24,000 tests. The improved diversity method? Still over 14,000. But Bayesian illumination? It found the exact same molecule in just 629 tests. I mean, wow, that is a massive, massive drop. This chart just makes it crystal clear. This isn't just a small improvement, it's a revolutionary leap. Look at those giant bars for the old methods, and then look at that tiny little bar for Bayesian illumination. It's doing the same job with a tiny fraction of the work. It's not even in the same league.
Let's just put a number on that. We're talking about a nearly 38 times improvement in efficiency over the original method. That means finding the treasure 38 times faster, using 38 times fewer resources. This is a total game changer.
So, why does all this matter outside of a computer science paper? Because a tool this powerful doesn't just stay as clever code on a computer. It opens the door to real-world breakthroughs that could affect all of our lives.
You see, faster, smarter molecular design means we could discover new drugs for diseases like cancer or Alzheimer's more quickly. It means designing better, more efficient materials for solar panels to help fight climate change. It means creating new diagnostic tools and just generally speeding up the pace of science across all of chemistry. The author of this study really sums it up perfectly. They say that Bayesian illumination sets a new baseline for the efficient and effective molecular optimization of small molecules. And whenever you set a new baseline that is this much higher than the old one, you open up a whole new world of possibilities. Which leaves us with this final thought to chew on. We've seen that this new method can be dozens, even hundreds of times more efficient. So the question we're left with is this. What breakthroughs that seem impossible today suddenly become possible tomorrow, when the very process of discovery gets accelerated by orders of magnitude? What problems can we finally solve?